In this video, we're going to look at how the remainder and factor theorem work in the context of helping us solve polynomials. So previously, we've looked at how to solve polynomials via polynomial division. You were told that a factor of a polynomial was some kind of linear or perhaps a quadratic, and from there you're able to polynomial divide, which would therefore give you the factorized form of a polynomial. But under those circumstances, you were given the factor. In this video, we're going to have a look at how we can use a specific kind of technique called the remainder theorem or the factor theorem to actually find those factors. So, what's going on? Well, first up, what is the remainder theorem? Well, the remainder theorem is simply an equation that will tell you the remainder of a polynomial division without having to actually do the division itself. And it is such that if you have a polynomial called f of x, and you were to divide that by some linear ax plus b, then the remainder after division is the exact same thing as if you had just subbed in the negative of your b term divided by your a term into your polynomial. So in this example here, we have a cubic divided by some linear. If we wanted to know the remainder after division, all we've got to do is figure out, what is b and what is a. So in this case, b is -2 and a is going to be 1, since those are the coefficients from our linear. And so you can see from there. So all we're going to do is sub that into our remainder theorem, f of -b over a. So negative of b, so -2 divided by a, where a is 1, you're going to have f of 2 as your remainder after division. F of 2 just means replacing every x in f of x with x equals 2. And so you replace all those 2's, you simplify, and that gives you a remainder of 6. So without having to do this polynomial division, you would know already off the bat that your remainder after division would be 6. This has another use case. Remainder theorem is itself an equation, and so if you're solving for some unknowns, then it could be used to figure out, or at least provide, one of the equations to solve one of those unknowns. In this case, we only have one unknown, and so when we do our remainder theorem on this, that's the only thing we need to do. So we have our polynomial, and we're told that the remainder is 17 when it's divided by x minus 3. So if I divide this thing by x minus 3, I get a remainder of 17. Well, using our remainder theorem, first things first, what is our a term and what is our b term? In this case, a is going to be equal to 1 and b is going to be equal to -3 just by directly comparing those coefficients. Subbing that into the remainder theorem tells us that our remainder should be f of 3 after everything has been simplified. But we also know that our remainder should be 17. So f of 3 is the same thing as 17. After expanding what f of 3 actually looks like, you can simplify and eventually get k equals 4. So it can be used to solve unknowns by providing you one of the equations to solve one of those unknowns. That brings us to factor theorem, which is how we use it in the context of helping us solve polynomials. Factor theorem is basically the same thing as remainder theorem, but it simply just says that if your remainder is 0, so if remainder theorem equals 0, then the linear that you subbed in there must have been a factor. Now, this goes back to just what is the definition of a factor, where a factor is simply just something that when you're dividing your number by a factor, there should be no remainder. That's what the factor is, what a factor is for any number. And that's no different for if it's a polynomial or if it's a linear or it's a whatever. So if our remainder theorem gives 0, we are certain that the linear that we subbed in there must have been a factor. So if you want to prove that a certain linear term is a factor of your polynomial, well, you just want to sub in that linear term, the -b and the a, into your remainder theorem and see that it equals 0. So in this case, we have x plus 1, so -b must be -1 and a must be 1. Our final result there is f of -1, and after plugging that into all the spots in f of x, you see that f of -1 is equal to 0. That result of 0 means that our x plus 1 must have been a factor of that cubic. Now, here's how this gets used for solving polynomials. Instead of proving that we have a factor, we can use it to find a factor. Now, off the bat, I'll warn you, this is kind of a guess and check approach. There are certainly ways that you can reduce the amount of things that you guess and check, which is what we're going to have a look at next. So, we have this cubic. It equals 0, and we want to solve for that cubic. A problem immediately arises in that we don't see an easy way to factorize this. We can't just take out a common factor of x. There is no linear that we're told it can be divisible by. We're kind of out of options, at least until now. One of the things we can do is apply factor theorem. And the way it works is that you go to the constant of your polynomial, whatever that happens to be, whether it's a cubic, whether it's a quartic. In this case, it's a cubic, and the constant is 6. All you're going to do is list out the factors, positive and negative, of that term. In this case, it's 6. So we're looking at plus minus 1, plus minus 2, plus minus 3, and plus minus 6. These are the factors that we're going to sub in, or at least these are the numbers that we're going to sub in to our factor theorem and hope that we get 0. And yes, I do say hope, because you're not guaranteed to get 0. My recommendation is to start out with the smallest numbers and then work your way up to the biggest numbers. And that's for 2 reasons. The first reason is that smaller numbers are easier to work with. And the second reason is that your assessors also know that smaller numbers are easier to work with, and so they're likely to choose numbers that are close to that list rather than further away from the list, because they don't want you spending an entire SAC or exam on just this question, testing factors until it eventually works. They want to kind of throw you a bone, so to speak. But okay, so we're going to test those numbers. If we start out with testing the smallest possible number, 1, we find that we get lucky here. Right? We immediately see that f of 1 is equal to 0. That result, equaling 0, we discussed earlier, means that we have a factor. Right? When the brackets, if you sub in a number into your brackets and that equals 0, that linear must have been a factor. So we found our factor. Now, we'll look at what we do with that in a bit. The next thing I want to show you is what happens if it doesn't work out. So I said you could test both positive and negative. If you were to test the negative version of that, you would set this equals 8. 8 does not equal 0, and so you would move on to the next number, which might be positive 2, for example. The good news is you only have to find one factor, which in this case we found in the brackets equals 1 does give us a remainder of 0. Now, what does that mean? Well, f of 1 equals 0. Factor theorem says f of negative b over a equals 0. So, by direct comparison, 1, this spot in the brackets, must be equal to negative b over a, the same spot in the brackets. 1 equals negative b over a. By convention, to make life easier, we're just going to assume that a equals 1. And so, when you assume a equals 1, you just get 1 equals negative b, or b must be equal to negative 1. So, we have our a equals 1 by convention, and b equals negative 1. The linear term, ax plus b, must therefore be x minus 1. So that's how linear. So by using factor theorem, we figured out what is this polynomial divisible by. The next step is to actually perform that polynomial division. Now, we've seen how that works already. I won't go into the specific details on how that works, but basically, you're taking that cubic that we had earlier and dividing it by the linear that we found using the factor theorem. If you don't get a result of 0, you've done the polynomial division wrong, or you've done this wrong, where you've equaled it to 0, or you found that it equals 0. So, from there, after you have your result after division, what this is telling you is that when you divide a cubic by this linear, you get this resulting quadratic. That is the result of the polynomial division, or at least this polynomial division. If you were to rearrange this left-hand side of the equation, it would just mean that you multiply both sides by x minus 1. And that's going to give you that this cubic is the same thing as this linear multiplied by this quadratic. Now, if you see my previous video on how this works, what you have here is a null factor law situation. Because you've got you've converted your additions and subtractions of terms into two things that are multiplied together, which would presumably equal 0 if you're trying to actually solve this polynomial. So we've seen that this cubic is the same thing as this right-hand side. And so if this cubic was equaling 0, then instead of saying cubic equals 0, we can say this product of terms is equal to 0. And from there, you just use null factor law like we've looked at earlier. So x minus 1 equals 0 from this one, and x squared minus x minus 6 equals 0 from that term. Solve those individually using whatever methods you like. Linear is nice and simple. Quadratic, I've elected to use a factorized approach, which, if you can spot the factors immediately, is of course the fastest way to go about it, where possible. So, in summary, you don't always have to do a polynomial division if all you're looking for is a specific outcome. Like, for example, the remainder. If you want to know the remainder, and that's all you want to know, then don't have to worry about doing the full polynomial division. Just have a look at your linear, do f of negative b over a, and that is your remainder. If you are trying to solve polynomials, then that's where factor theorem will apply. So you're simply going to test the coefficients at the end. So if we go back to what that looked like, if your final value, the constant at the end, is a +6, then you're going to test all the factors of 6, positive and negative, until you get one that equals 0. From there, you assume that a equals 1, compare the two things in the brackets, and that becomes your linear term. Polynomial divide, rearrange the polynomial division, and solve using null factor law. So there's a lot of steps there. There absolutely is a lot of steps there, which is why this typically doesn't show up on SACs or even exams. I have seen remainder theorem show up in an exam before as a multi-choice. Factor theorem, not so much, because, well, you've seen how much it takes for a full polynomial to be solved using this approach. You're doing some guess and check, which may take a while on its own, depending on how far down the list they've chosen their factors to be. Then you've got to do a full polynomial division from that, and then, well, this step here isn't too much work, but it is still an additional bit of work on top of that. So it tends to take a while, but unfortunately we don't really have a better option afforded to us. That's about all for this one. Thanks for joining.